Hi, my name is Nassim Yanofsky, and we're up to section 6.1, Monoidal Functors and Natural Transformations. Okay, so this is the beginning of chapter 6, so let's just put everything in context. So, chapter 1 through 4, we learned all about categories. Chapter 5, we learned about there's categories with extra structure called a monoidal structure. Very nice. And now chapter 6 is called relationships between monoidal categories. Okay. So how does these functors and natural transformations between categories which have this extra structure, how do they relate with each other? Let me put it another way, sorry. You have a functor from one monoidal category to another monoidal category, okay? So we know what a functor is from a category to a category, but what is it from a monoidal category to another monoidal category? In other words, what does it have to satisfy, okay? And so this is what we're going to do the first section, is talk about the different types of monoidal functors and monoidal natural transformations. The idea is as follows, to keep in mind, let's say you have a monoid. So this is a set with extra structure. So it's a set with, I don't want that operation, a set with a multiplication and an identity, okay? And you have another monoid with another operation and another identity, okay? Okay, so what do we demand? So what is such a monoid homomorphism? Well, answer, it's a function from this set to this set, which satisfies the following two requirements. F of x dot y, okay, so that's in here, should equal to f of x dot, comma, that's in here, f of y. In other words, the function, the monoid homomorphism, should respect, that's what it means to respect the multiplication. But another thing we want also is f of e, that's the unit over here, should equal to f of e prime. Okay, so this is for sets with extra structure. But we're not interested in sets with extra structure. Now we're interested in categories with extra structure. So we're going to have to look at the analog for this in terms of functors, not functions, but functors between categories. Okay, so let's get started. Okay, but keep that in mind. Okay, and the idea is as follows. So what's a monoidal functor? So let's just write, so this is a definition. Okay, and so you have the following. You have a category so this is all the data of a monoidal category. And here's another monoidal category. Let's just remember, this is a category, this is a tensor product, this is the unit, this is the reassociator, the right unitor, the left unitor. Okay, so you have two of them. Well, what is such a thing? Well, it's going to be a functor. It's going to be something called a funnel, okay, a mapping funnel, and a unital funnel, okay, which we write as V. Okay, so let me show you what these are. Okay, that's a Greek letter. Okay, so what it is as follows. Well, it's a functor from A to A prime, okay? But it has these two other things that these two other things, which is, this is called a mapping funnel, okay? And the idea is as follows, you'll see it in a second, but this is, if you have two objects here, A tensor B, sorry. Okay, so you can map f of A, which is in here, and you can map f of B, which is in here, okay? And then you can take the tensor product of them, which is in here. Fine. But another thing you can do is you can do f of A tensor B. Okay, A tensor B is in here, f of that is in here. So this morphism is in this category, and we call this morphism T, tau of A comma B. Okay, and the idea is as follows. Think of a funnel. A funnel is like this thing that, you know, it's wide on the top and it goes into one pipe or something. So you have two different things and they funnel into one thing. Okay. Now, this is the analogy of what I had here a second ago, where this was equal. Okay, you have one operation, you have another operation, and they're equal. Well, we don't want equal. We want a morphism like that. Okay, and we'll give a name for that later on, what type of morphism, et cetera, et cetera. Okay, the other thing is called a unital funnel, and it goes as follows. Just let's do the category. Let's do the, remember we had E prime is equal to F of E. So we're going to want something along that line. So we're going to have as follows. We're going to have I prime of F of I. We're going to call this mu. I don't know what the Greek letter is. V, we'll call it V. Okay, so it's a functor, but it has these two natural transformations, natural A and B, natural, well, it's not, morphisms between these things, between I and I prime, between two I primes, et cetera, so it's natural. But now we have coherence conditions. Okay, so we have coherence conditions, which are going to amount to the following fact. We want these guys to get along with the structures in here also. Okay, so let me tell you what the coherence conditions are. Ready? So here's one. F of A, F of B, F of C, F of A, F of B, F of C. Okay? Boom, 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 boom. Tensor product. I'm sorry, this is tensor product prime. This is tensor product prime. Okay? So this is alpha prime. So this is just a reassociator of these three different objects. Nothing to talk about. Okay, great. Now, I'm building up this diagram. Okay, so here's another thing we can have. We can have A tensor B tensor C, like that, or F of A tensor B tensor C, like that. Okay, so here's two things in the first category. I'm sorry, three things in the first category, three things in the second category, associated differently. And so this is alpha of the things in the first category of A, comma B, comma C, and you have F of that. It's a functor of that. Okay, great. Okay, this is really F of A, comma F of B, comma F of C. We'll leave that out. Okay, now another thing you can do is as follows. This is identity on F of A, tensor tau. Okay, and let's bring these two things together. Let's funnel these two things together. So we're going to get F of A, tensor prime of F of, now bring them together. So that's B tensor C, like that. Okay, so that's a tau of B comma C. On the other hand, we can do the same thing here, funnel these two together, and so we get this. This is tau tensor prime, that's a tensor prime of identity, okay, and so this becomes f of a tensor, not prime, b tensor prime f of c. Okay, great. Now we have two more maps like this and like this. This says funnel this together. So this is now tau of A, comma, B tensor C. And this is tau of A tensor B, comma, C. Bring it all together. Okay? So this is called the hexagon coherence condition. It's a hexagon coherence condition. 1, 2, 3, 4, 5, 6. There are 6 things. Hexagon coherence condition on monoidal functors. Okay, and basically what it's saying is that the alphas has to get along with the taus. Okay, so that's very nice. Okay, but I want to just say one thing, and we're going to see this a little bit later. Okay, and the idea is this is a statement about 2 letters funneling into 1. This is a statement about 3 funneling into 1. I'm sorry, 3 funneling into 1. So that's what we're doing. And we're going to see later on about 4 funneling into 1. Okay, and we'll get to that later on. But you see a progression: 2, 3. We'll see later on 4, and we'll see what that's all about. Okay, great. But I'm sorry, we're not finished yet. We need 2 other requirements. Okay, I'm going to write one of them, and it goes as follows: f of a tensor prime of I prime. Okay, so this is happening in the second category. Okay, we can do identity tensor V. Okay, and so what is that? F A tensor prime F of I. Okay. Okay, now bring these together and we get F, so this is a tau, so this is F of A tensor I, okay, and now this is a row, let's just make sure, this is an F of row, okay, so F of row, this is going to go till A, I'm sorry, F of A. Okay, and this is a, by the way, yeah, this is a row prime. Okay, so what that says is this tau gets along also with this unit funnel, and it also gets along with the 2 rows. Okay, 1 row from the source category, 1 row from the target category. Okay, and there's an entire other diagram, not about row, but about lambda. Okay, so that's it. Okay, so finished. That's it. That's the definition of a monoidal functor. So let's just go through it again. It's a functor that has this funnel of bringing in the tensor product into 1, okay, in other words, okay, and the other one is the unit, making the unit work out nicely, and it has to satisfy this coherence condition and these 2 coherence conditions about rho and lambda. Okay, and basically these are ways of showing that the natural transformations cohere with each other. They get along with each other. Okay, and we'll see why it's needed in a minute. Okay, I would like to show show you another way of looking at this relationship in a second. I'd like to show you another way of looking at this. Okay, so think of this. Here's you have, sorry. Let's go back to monoids. So we had the following two requirements. F of A star B is equal to F of A star prime F of B. Capitals, smalls, what a pain in the neck. Okay? Okay, we had another requirement, namely F of E equals E prime. I'd like to draw this for you as a commutative diagram. Okay, I'd like to draw this as a commutative diagram. So this is basically M times M, M times M, I'm sorry. No, sorry. Okay. So I'm drawing the top one as a commutative diagram. We're doing lowercase, we're doing lowercase. F, and this is F times F, and that's a prime. Okay, so saying that this commutes, I'm sorry, saying that this is equal to this is saying that this commutes. Okay, and now I want to do a similar diagram for this. Basically, pick out one object set, picks out an M over here, picks out the unit over here, and the one object set picks out the unit over here. If you want, we could do this. Okay, and then we have this F is here, and basically what that says is pick out the unit in M, do F of it. That's the unit in M. Do F of it. That's going to be the unit of this. So in classical algebra, we have these commuting. Okay, let me just make sure I got the bottom. Yeah. We have these commuting, and that's very nice. But it's not what we want, okay? Because now we're moving up, and we're not talking about a monoid, we're talking about a category with higher structure. So the way I want to show this is as follows. So this is A cross A. This is the tensor product. This is A. This is A prime cross A prime. This is the tensor product. And this is A prime. Okay, and now we're talking not about functions, but we're talking about functors. And so we have that. Okay, now, we don't want this to commute. If we wanted this to commute, then we'd have F tensor F of, there would be an equal. We don't want it to commute. What we want is a natural transformation from here to here. So notice, we've boosted up this diagram. Before it was a diagram of sets, now it's a diagram of categories. So here's a functor, here's a functor, here's a bifunctor, here's a bifunctor, here's a functor, etc. This is in the diagrams. So this is a natural transformation, tau. Okay? Okay? And it has to satisfy a certain requirement. But I want you to see this as a generalization, whereas in regular, when we're dealing with sets, so you have sets and functions between sets. That's very nice. Okay, but you have nothing between functions. But if you boost it up to categories, you have category, 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 functor, 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 functor. But now you could talk about natural transformations between functors, and that's exactly what that is. Okay, similarly, okay, this is the one object category. This is the category A. This is the category A prime. This is the functor F. Okay, and this chooses the unit of the monoidal structure. This chooses the unit of the monoidal structure. Then we don't want this necessarily to commute, although it can commute, by the way. We just want an isomorphism here, and we call that V. Okay, so this is stepping stone from sets to categories. Okay, great. It's very important to understand hence the term higher category theory. I'm sorry, higher algebra. So the diagrams we had before were just diagrams. They were very nice diagrams, but now we have higher diagrams. Higher algebra, higher dimensional algebra. Okay, great. Now, question, what happens if your monoidal category, if your two monoidal categories are strict monoidal categories? Well, in that sense, what happens is as follows. The reassociator is the identity, and so we're going to have this. F of A tensor F of B, sorry, tensor prime F of C, no other parentheses because it's strictly associative. Okay. And now, hold on. Same thing down here. Okay, so this is going to be F of A tensor B tensor C. Again, no parentheses because this is strictly monoidal. Okay, and now we want this to commute. So again, if you're dealing with monoidal categories that happen to be strict, you can strictify, or you can crunch this hexagon to be this diamond. Okay, and so this is identity tensor tau, and this is tau tensor identity, and this is tau, and this is tau. So you take the hexagon, you shrink the two reassociators to be the identity, and so that becomes that. Okay, great. So that's why I left this here. So now we can see that. I just shrunk it. Great. As always, we have a hierarchy of monoidal functors. Okay, so the thing I just described to you, I'm sorry, there's a million names. I'm going to have to look them up because I can't keep up with all the names. Okay, the thing I just described to you is sometimes called a weak monoidal functor or a lax monoidal functor. So a weak monoidal functor or a lax monoidal functor. Okay, but that is just the beginning of the story, because we can also talk, notice we had two things funnel into one, but you can also talk about, so this is one thing, you can also talk about F of A tensor A prime going to F of, maybe that should be a B, just for uniform, F of A tensor F of B, that's a tensor prime. Okay, so you can't call this funneling anymore because funnels take different things and they all shrink to one, but here we're taking one thing and we're spreading it out. I don't know, call it a spreader if you like. Okay, but the real fancy name for this, okay, let's do another one. You also need F of I to go to I prime. Okay, so again, I switched the morphism. Notice they're not isomorphisms, so it depends which direction. So these are called, these also have names, and they're also called, they're called oplax monoidal functor. So let's go, just write the word oplax. So it's opposite, so it's oplax, okay? Also called comonoidal functor, I don't know why, or opmonoidal functor, or colax monoidal functor. Oplax, colax, very nice. So again, the weak monoidal functor can go this way or it can go that way. That's it. Okay, then more. So all these are just, we're assuming the monoidal functor is a morphism. But we could also have a strong monoidal functor. Okay, and that is where f of A tensor B is isomorphic to f of A tensor prime f of B, and f of I is isomorphic to f to I prime. Sorry. Okay, so this is called a strong monoidal functor, and simply because the funnels are isomorphisms. Okay, and then there's something else called, ready? So that now a fourth definition, strict monoidal functors. That's where these are actually equal. Okay, so again, there's this hierarchy of uniqueness of morphisms. Okay, I just want to say, when you're dealing with a strict monoidal functor, then those two diagrams that I just had here, diagrams of categories and functors, in fact commute. Okay, in other words, this is equal to this. Okay, when we had strict, this would be isomorphic to this, and in general, this is a lax monoidal functor, and this is an aplax monoidal functor. So you can draw all these different definitions with these two diagrams like that. Okay, and the main point is they show up all over. Every single type shows up all over. We stressed the weakest version, but we're going to see later on every single type shows up, every single type is important. Okay, and the point is, this expresses the power of these ideas, and we have to keep ourselves, we have to be able to use all these different ideas very nicely. Okay, so let's see some examples before we get busy. Okay, this is a nice example, but this is something we mentioned before. You have r, comma, plus, comma, 0. So this is the real numbers with addition with 0. So that's a monoidal. That's a monoidal category. You can think of these as, this is an ordered category, totally ordered category. And you can add two real numbers, and you can, when you add to 0, you get it. By the way, that's a strict monoidal category. Okay, the plus is strictly associative. You also have r plus, that's the positive real numbers. Okay, multiplication, and 1, the unit here. So here's two monoidal categories. Okay, we mentioned them before, but now I want to show you how they're related. Okay, and so the idea is as follows. These are strict monoidal functors. Okay, so b is some number. What do we assume? We assume b is greater than 1. b is greater than 1. That's the base. And this is log, base b. Okay. And so, what these are, well, this is an isomorphism, that's first of all. But the second of all is, this is raising, take x, raise it to the power b. Logarithm is the inverse function of that, and it goes as follows. Okay, but what I want to do is I want to look at the funnels from this point of view. The funnels are strict, so we're going to have equal, but basically what it says is b of x times y, plus y is equal to b of x times b of y. So something we've seen in 4th grade, maybe 6th grade, we've seen this in 6th grade, b of x plus y is b to the x times b of y. That's just saying that your natural transform, that your monoidal functors are strict. Okay, and of course the opposite is true too. So logarithms of x times y, so this we may have learned in 9th grade, is equal to logarithm of x times logarithm of y. I'm sorry, plus logarithms of y. Again, strict. By the way, let's just do the unit. B to the 0 is equal to 1. Okay? That says that's strict on the units, and log of b to the 0 to the 1. What do you have to raise b to in order to get 1? Answer 0. So again, something we've seen in elementary school, we can see it as an example of a strict monoidal functor. Very nice. That's a nice example. Okay, next. One of the last things we did in section 4.1, I think, was talk about set and k vector spaces. Okay, and we said to every k vector space you can forget the k vector space. You can forget the addition, and you can forget the scalar multiplication. You just have the set of vectors. Another thing is, so you can forget that. Another thing is f. You have the free. Take a set. Think of it as a set of basis. Take the free of the free vector k vector space over that, and you go this way. Okay. Main point. That's a left adjoint. Hold on. So that's what we did at the end of section 4.1, I think. I'm sorry. The fact that maybe we did it at the end of 4.4 where we talked about a junction. Very nice. Okay. But that's looking at sets and k vector spaces as just categories, but they're not just categories. This has disjoint union, okay? This has disjoint union, and the empty set is the unit. Okay, and k vector spaces also have a direct product where the 0 vector space is in here. Okay? Okay, great. So, turns out, I don't know, V. What do I call it here? Tau prime V prime. Turns out that we can up our game, not only talking about the free sets and the forgetful functor of a k vector space, but you know what? This has extra structure. I can take a basis, I can take another basis, 2 sets, and I can look at the free vector space over this and the free vector space over that, and see how it relates to the free vector space of this union, this disjoint union that. Okay, so that's what that's all about. Similarly, I could take two vector spaces, okay, with a direct sum, okay, and see how it relates to that. Okay, now, once we do this, we still have to go on, and we have to talk about to what extent is this strict, is this strict, is this strict, is this strict? And some are and some aren't. And in the book I go through each one and showing why they are strict and why they are not strict. Hold on, that's just half of the story. Because we saw another monoidal structure on this, and we saw another monoidal structure on this. Rather than erasing, let's rewrite it. So you have sets, and you can talk about Cartesian product. And again, no, sorry, the unit is any one object category. I'm sorry, one object set. Okay, and then you have K vector spaces. I think I might have talked about C vector spaces. Okay, and we have the tensor product of K vector spaces, and we have K as the unit over there. Okay. Okay, so set okay, well, guess what? There's functors going back and forth like that. Okay, main point here, I like this, this is a good point. You have two sets, you have two bases. Okay, take the Cartesian of them, okay, and that's the tensor product of the two vector spaces that you get. And again, you have to go through what is the funnels, both funnels, four funnels, unit funnels for F, unit funnels, and tensor funnels, and unit funnels for this, and you have to go through each one of them and see whether they're strict and whether they're just a weak morphism, and whether they're the identity, whether they're isomorphism or whatever. Anyways, I do go through that. Very nice. Okay, so main point. The world we saw connecting sets and vector spaces, it respects these two different operations. And we're going to have to go through these two different operations again. To tell you the truth, even that is just the beginning of the story. Great, let's go on. Let's say you have a monoidal category here, and you have a monoidal category here, and you have a monoidal category here. Okay, and let's just do this. This is F tau V, and this is F prime tau prime V prime. Okay, well, I'd like to know how these compose. Okay. Okay, so the way they compose is very simple in terms of the functor. So this functor composes with this functor. So this is going to be F, I don't know, double prime, which is equal to F composed F prime. That's the functor. Okay, how about the natural transformations? I'm sorry, you're right, how about the natural transformations? So what's the funnel of the funnel in some sense? Okay, so we're going to call it T double prime, and I'll show you how to do it. And also we're going to have the uniters, so we're going to have that as V double prime. Okay, so this is the way we show how it composes. Later on, I'm probably going to forget to say it, but we have to show that not only does it compose, but it's associative. So you have to go through, and that's going to be a pain in the neck because you're going to have a lot of things to worry about, but that's okay. Okay, so let me just show you how this works. Okay, and it's very nice. It works as follows. Take F composed F prime of a tensor. No, sorry. Tensor. Now see, this is happening in here. So this is tensor prime of F composed F of B. Okay. So the first thing you want to do is, whoops. I'll give you the name for this in a second, but basically what you want to do is you want to have F bring together, I'm sorry, I don't want to write it with the compose, I want to write it like this. Right. Okay, so the first thing we're going to do is I'm going to have this is F prime of f of a tensor prime f of b. Okay, so here's one element in A prime. Here's another element in A prime, and we're going to bring that together to be one element. This is now in A prime, and f of that is in here. So this whole thing is in here. Okay, so what should we call this? We should call this tau prime of f of a, no, you're right, no, f of a, comma, f of b. Okay, that's exactly what it is. Okay, but now I want to bring this together. So we do it as follows. Okay, so we do this as follows. So this is going to be f of a tensor b. Main point, a double tensor, a single a double prime, a single prime, a without anything, and this is f of prime. Okay, now so what's this? This is f prime of tau, this tau. This is bringing these two things together into one. Okay. Okay, so we had two of them, we bring them together. By the way, this is the higher algebra version of proving that the composition of two group homomorphisms is still a group homomorphism. Okay? This whole map, this composition of map, should be called tau prime of a comma b. Okay, great. And there's a nice one also for the uniters. Okay, it's not done in the book, but we can do it now. So let's do it. So we have f prime of I maps to f prime of I prime, which maps to I double prime. So this is a V and this is a V. So this is probably V prime and this is V. Maybe that's F prime of V. Okay, hold on. What's left? We're not finished. Okay, because we have to show that this composition satisfies the hexagon condition. Okay, it's a little bit too ugly and big to retype, so we have the following. It's on top of page 286. It's a big ugly thing, and here you have the tau double, the alpha double prime. Here you have the alpha regular. Here, here you have regular alpha, and here you're going to have alpha prime. Or something like that. Anyways, main point, we're going to assume built in here you have hexagons. We're going to assume the triangles commute out of units or definitions, and it all works out very nicely. Okay. Okay, so it composes. So monoidal functors compose. Not only they compose, there's a unit, I don't know what the hell that was, there's a unit monoidal functor, okay, and it acts nice like a thing. So guess what we have? We have the category of monoidal categories. Okay, we're going to fix this, we're going to adjust this in a minute, we're going to add more, but that takes care of that. Great. let's go on. Not only did we talk about monoidal categories, we talked about symmetric monoidal categories. What's a symmetric monoidal category? That not only do we have things like this, but we can talk about swapping those two things. Okay, so we want to talk about monoidal functors between symmetric monoidal functors. I'm sorry. We want to talk about monoidal functors between symmetric monoidal categories. Okay, and the idea is as follows. Okay, so we're going to have to worry about, so you're going to have a monoidal category with a symmetry. We're going to leave out all the other stuff because we know we have it. We have B, a monoidal category with a symmetry. We'll call that. Okay, great. And now we want a functor between them. Okay, and the functor will have a tau. Okay, yes, it'll have a unital funnel also, but let's not deal with that right now. Okay, well, we want these two guys to respect this tau, or they should respect each other. And let's do it. You ready? So we have f of A tensor f of B f of A tensor B, that is tau of A comma B, but we could also swap them. A comma B, I'm sorry, f of, so this is that's gamma prime because this is in B, f of A is in B, f of B is in B, so that's gamma prime, so this is going to be f of B tensor, it should probably be a prime, that should be a prime, f of A, and guess what? We can do tau B comma A. No. Yeah. And so this becomes what? F of B tensor A okay. And this, notice AB here, BA here, so this is F of gamma of A comma B. Yeah. So by respecting it, we mean that this should compute. Okay, so now we have, so now I just defined what I think it's called a symmetric functor, a symmetric monoidal functor between two symmetric monoidal categories is. Okay, great. Good. Let's put all our information together because it's getting too hard to see. And we're going to start building these diagrams showing you all our information. So it goes as follows. I'm going to draw it over here because we're going to come back to it and we need to keep it. So we're going to make some space and we're going to make this diagram very clear. You ready? Okay. So we have monoidal categories. I'm trying to keep up with the way I call it in the book. So monoidal categories. Okay, so let's just say what the objects are. The objects are monoidal categories, and the functors are monoidal functors, and the morphisms are monoidal functors. So here we had the objects are categories, and the morphisms are functors, but now we've added monoidal structure to it, so we have this. Okay, there is a subcategory of this called, big name, strict monoidal functors, strict monoidal categories. Okay. I'm sorry, in the book I say, I want strong monoidal categories here. I'll need it later for that. So I don't want just lax. I want to keep it to strong, where you can make your own notation, but let's do it like this. So this is strict monoidal categories. Let's see what these are. Well, they're categories with a monoidal structure that's strict. So these are special types of monoidal categories. Here, the alphas, so here's the alphas are one, are the identity. The alphas, the reassociators, are the identity. Great. Okay, now in this category, the functors are strict monoidal functors also, so we need that isomorphism. Okay, great. But we had other things called symmetric monoidal categories. Okay, let's just remember what those are. So those are monoidal categories where you could also have the swapping. So there's a natural transformation to swap. But the relationship between this is not a special type of monoidal category. Rather, there's a forgetful functor. So this is an inclusion. This is a forgetful functor. So again, the idea is, given a monoidal category with the ability to swap A tends to B tends to A, if you forget the ability to swap, forgetful functor, then you get a monoidal category. And there's strict, there's two adjectives here, strict and symmetric. I want to make sure that I have it right. Strict symmetric monoidal cat. Okay, so what's that? That is a monoidal category where the reassociator is identity. In other words, the tensor product is associative on the nose, okay? But there's also the ability to swap, okay? And you have to worry about the morphisms there. And again, there's a forgetful functor like this. So I'm sorry, there's a lot of things to keep track in here. You want to keep track of how strict your monoidal category is and how strict your functors are. And you have extra structure in a lot of them. Okay, so we're not only talking about monoidal categories, we're talking about that too. And that's just the first two layers of our structure. So this is about monoidal categories and monoidal functors, but just like there's categories, functors, and natural transformations, which we saw in chapter 4, so too there's monoidal categories, there's monoidal functors, and there's monoidal natural transformations. So let's do that. So let's do that. I'm going to keep this for a second. Okay, so you have a tensor alpha. You have B tensor prime, alpha prime. You have F tau V. That's one monoidal functor. You have, what am I doing? Which one? F prime, tau prime, V prime, another monoidal functor. Guess what? Natural transformation. Okay. And here is mu. Okay. So that's a natural transformation. So again, these are functors between categories. We have natural transformations between functors between categories. But this is a special type of functor that satisfies these natural transformations. This is a special type of functor that satisfies these natural transformations. We want this natural transformation to get along very well with those. Okay? And here's the requirement. Okay? It goes as follows. Well, let's just go over here and write it, what we want usually. So we usually want mu of little a goes from f of little a to f prime of little a. Okay, and this should be natural, which means if there's a map from a to a prime, we should respect that. Okay, great. That's what a natural transformation is. But now we want to take into account the taus and everything, the taus and the alphas. So we're going to leave out the alphas for a minute because we don't need them right away. We don't need them. Maybe we'll talk about strict, or we'll talk about strict monoidal categories, but let's leave them out. Okay, so let's talk about this. Well, what we want is f of a tensor f of b. Okay, I'm not going to look at the book. Let's work it out by ourselves. So here we want mu of a tensor mu of b. Okay, and so this should be what? F prime of a tensor f prime of b. That's exactly what the mu's do. They go from f to f prime. So that's exactly what we did here. Okay. Classically, or chapter 4 and chapter 5, chapter 4, we didn't care about the tensor product, but now we have to care about the tensor product. Hold on. Now we have tau. What does tau do? Tau brings together things like this. So this is going to become f of a tensor b. So this is tau of a comma b. Okay. And this also has a tau. I'm sorry, this also has a tau. F prime also has a tau, so this becomes f prime of a tensor b. Oh, let's get our tensors correct. This is tensor prime, this is tensor prime, this is tensor, this is tensor. Okay, let's do this. This is tau prime, that's this guy, bringing the f primes together. This is a comma b. Okay, great. Now what the hell is this? This is mu of a tensor b. Sorry, let's do that a little bit prettier. Mu of a tensor b. Okay. Okay, one other requirement. Okay, let's just remember, we have an I prime, and this is f of I, and we call this V. We also have f prime of I, which we'll call, this is V, this is V prime. Okay, well, this is mu of I. So we want this to commute also. Okay? Okay, great. So if a natural transformation satisfies these two requirements, in other words, it respects these extra natural transformations here, then we call it a monoidal natural transformation. A monoidal natural transformation. Okay? Great. And just like we talked about this is the category of categories, small categories, locally small categories, and functors. And then we said, you know what? Let's go up one level. So this was the two category, and we talked about two categories, the two categories of categories, functors, and natural transformations. Well, guess what now? Boom, 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 boom. Now we have not categories, but two categories and functors in between them. Okay, so let's go through this. This is going to be the category of monoidal categories, monoidal functors, and monoidal natural transformations. This is going to be the same thing, but with extra symmetry. By the way, no requirement whatsoever. Let's say this had a symmetry in it, and this had a symmetry. We don't make any requirement that that should commute. So if we had the FAB, we swapped it, there would be no extra requirement. Okay, in the book I write, a symmetric monoidal natural transformation is a monoidal natural transformation between symmetric monoidal categories. No additional requirement is needed. Okay, and so you have this commutative diagram of two categories. Now I admit, you have to walk around with a paper that has all these definitions going on. There's a lot of different definitions going on here. But we are finished. Oh, I'm sorry. Hold on. No, we have examples. So there's a lot of different structures going on. Again, categories, natural transformations, and categories, functors, and natural transformations. That's 3 levels of functors. Each one of these has 3 levels of functors, and you have to keep track of all these different coherence relations, etc., etc. The idea is, once you get used to it, it's not so hard, because what you have to do is you have to say, okay, what extra structure do I have? How do I respect that extra structure? Respecting that extra structure is a coherence condition. Okay, so let's do some examples of all these things. I did some examples, but the rest of this section is just more examples. That's all we do is examples. Okay, so the examples come in lots of different shapes and forms. I want to show you, well, when we did section 5 when we did the advanced linear algebra, we had this whole thing, sets and finite sets and complex vector spaces and finite dimensional complex vector spaces, okay? And then we had complex matrices here, and we had unitary matrices here, okay? Let's just finish this off. We have Hilbert spaces here, okay, and U-Hilbert spaces here, and finite dimensional Hilbert spaces, and finite dimensional unitary Hilbert spaces. Okay, and lots of maps. So this is the free thing, that's an adjunction. There's a free thing, there's no forgetful functor. This is an inclusion of this into this is an inclusion into this and this. This is an inclusion, but an equivalence of categories. Complex matrices is the same thing as finite dimensional complex vector spaces. This was just looking at all unitary matrices, not all matrices. So this is an inclusion of this. Okay, and this is an inclusion of this, but not only an inclusion, but an equivalence of categories. Okay. Damn. This is unitary matrices. Okay. We have forgetful functors here. We have forgetful functors here. We have inclusions here. Inclusions here. Okay, so this was something we had at the end of our discussion. it brings in a lot of different things. We talked about that already. Main point is, for every one of these categories, there are two structures. There are two monoidal structures that we have to talk about. Sets with a disjoint union, sets with a product, Cartesians with vector spaces with a plus and direct product and monoidal tensor product. Same thing with there. Hilbert spaces are vector spaces with extra structure. We have forgetfuls, so we have to talk about that. Okay, great. So there are two diagrams like this. One with a monoidal product, one with a direct product with all of these. Okay, and so it expands from a regular thing into something else. Okay. Great. So, and of course, you have to go through every one of these and see what the funnels, to what extent are the funnels strict or weak or co-weak or oplax, etc., etc. Okay. Another thing. We talked about circuits. We talked about Boolean functions. And we talked about Boolean matrices. Okay, and the idea is as follows. These are three ways of talking about things, and they're related. These are three ways of talking about, well, there's a circuit. You could talk about a circuit as a type of Boolean function. Every circuit gives you a type of Boolean function. Again, the circuits are true and false. Well, that's Boolean 0 and 1. Okay, and you can also talk about them as Boolean matrices. But now we have a new thing, because now we have a disjoint union of two circuits. So let's just remember what that's about. A disjoint union means you have a circuit with a lot of different wires coming in and a lot of different wires going out. You have another circuit with a lot of different wires going in and a lot of different wires going out. Well, you have the disjoint union of them. That goes here. Okay. You could also take the disjoint union of two Boolean functions. Main point is disjoint unions here go to Boolean functions where the first inputs are determined by this circuit and the second inputs are determined by this circuit. And also, you could talk about a Boolean matrix that corresponds to this, and that will be up here. This will be 0 and this will be here. And then there will be a Boolean matrix that corresponds to here, and that will be over here. Okay, so main point is not only do we have these three ways of talking about them, but if we up our game and also talk about how these circuits are joined, okay, and again, not only sequential circuits, but parallel circuits, then they all talk about it the same way. Okay, I don't really talk about it in the book, but this actually has to do with quantum computing also, when you have two different circuits, etc. Okay, last thing, the last example given is a fairly elaborate example, but basically it's talking about circuits like before, but they're logical circuits, and now we have logical formulas. Okay, and so we have a functor like this. I don't think this functor was described before, okay, but we could have described it before. But this is a little bit more complicated. This is, the objects and the morphisms are a little bit more complicated, but the main point is as follows. For every circuit, you have a logical formula that describes the circuit, and again, if you have parallel processing of circuits, well, that's going to correspond to a sequence of logical formulas. Okay, and the main point is this has a monoidal structure. Okay, this has a monoidal structure. and this functor L, which goes, that is, respects those monoidal functors. So again, so let's just recap what we did today. Again, we've seen functors, we've seen monoidal category structures, and now we're talking about monoidal. We're talking about functors that respect those monoidal category structures. Okay, foreshadowing. This is 6.1. Now that we have this notion of relationship between monoidal categories, what we're going to do is what's called coherence theorems, which are theorems that state how you can change one monoidal category into another monoidal category. And again, you need the notion of functor for that. So that's why we have to do that. That's section 6.2, where we're going to talk about coherence theory. That's a fairly complicated chapter. It's going to take us time to do that. Okay, 6.3 is another question. It's another topic called when coherence fails. In other words, this is very nice dealing with this pentagon that commutes, making a monoidal category. But what happens if the monoidal category doesn't commute? And that whole chapter is a short chapter where we talk about this, all the definitions I gave here today, and I gave a hell of a lot of definitions. All the definitions are not built in stone. They're subject to different things. In other words, if you have a phenomenon that needs this definition, you use this definition. If you have some type of phenomenon that needs that definition, you have to use that definition. Nothing is etched in stone, and that's what we're trying to show there. Okay, and finally, the last section is about duality theory. Okay, it's a mini course on duality theory. We have all these different categories, we have all these different operations, and we're trying to bring them all together with so this is going back to lattices theory, Boolean algebras, semi-lattices and stuff like that. But think of them as categories with morphisms in between them. You get a lot of this duality stuff. Okay, have a wonderful day.